Section 13.1, the solution process. A solution is formed when one substance disperses uniformly throughout the other. As we noted in the introduction, solutions may be gases, liquids, or solids. Each of these possibilities is listed in Table 13.1. The ability of substances to form solutions depends on two general factors. One, the types of intermolecular interactions involved in the solution process, and two, the natural tendency of substances to spread into larger volumes when not restrained in some way. We begin our discussion of the solution process by examining the role of intermolecular interactions. The effect of intermolecular forces. Any of the various kinds of intermolecular forces that we discussed in Chapter 11 can operate between solute and solvent particles in a solution. Ion dipole forces, for example, dominate in solutions of ionic substances in water. Dispersion forces, on the other hand, dominate when a nonpolar substance such as C6H14 dissolves in another nonpolar like carbon tetrachloride. Indeed, a major factor determining whether solution forms is the relative strengths of the intermolecular forces between and among the solute and solvent particles. That is, the extent to which one substance is able to dissolve in another depends on the relative magnitudes of the solvent-solute, solute-solute, and solvent-solvent interactions involved in the solution process. Solutions form when the magnitudes of the attractive forces between solute and solvent particles are comparable to or greater than those that exist between the solute particles themselves or between the solvent particles themselves. For example, the ionic substance table salt dissolves rapidly in water because the attractive interactions between the ions and the polar water molecules, the solute-solvent interactions, overcome the attraction between the ions and the solid NaCl, and between the water molecules and the solvent-solvent interactions. Let's examine this solution process more closely, paying attention to the various attractive forces. When sodium chloride is added to water, as in Figure 13.1, the water molecules orient themselves on the surface of the sodium chloride crystals. The positive end of the water dipole is oriented towards the chlorine ions, and the negative end of the water dipole is oriented towards the sodium ions. The ion dipole attraction between the ions and the water molecules are strong enough to pull the ions from their positions in the crystal. Once separated from the crystal, the sodium and chloride ions are surrounded by water molecules, as shown in Figure 13.1. We learned in Section 4.1 that the interactions such as between solute and solvent molecules are known as solvation. When the solvent is water, the interactions are referred to as hydration. In addition to the solvent-solute interactions, the ion dipole interactions between the water molecules and the sodium and chloride ions, and the solute-solute interactions between the sodium and chloride ions in the solid, we must consider one other interaction, the solvent-solvent interaction, in this case the hydrogen bonding between the water molecules. In forming the solution, the water molecules must make room for the hydrated sodium and chloride ions in their midst, causing some water molecules to move apart. Energy changes and solution formation. We can analyze the roles played by the solute-solvent, solute-solute, and solvent-solvent interactions by examining the energy changes associated with each. Let's continue to analyze the process of dissolving sodium chloride in water as an example of how energy considerations provide insight into the solution process. We've observed that sodium chloride dissolves in water because the water molecules have a strong enough attraction for the sodium and the chloride ions to overcome the attractions of these two ions or for one another in the crystal. In addition, water molecules must separate from one another to form spaces in the solvent that the sodium and chloride will occupy. Thus, we think of the overall energetics of the solution formation as having three components associated with breaking the solute-solute and the solvent-solvent interactions and forming the solute-solvent interactions, as illustrated schematically in Figure 13.3. The overall enthalpy change in forming the solution, the heat of solution, is the sum of the three associated with these three processes. The heat of solution is equal to the heat of the solvent-solvent, the heat of the solute-solute, and the heat of the solvent-solute interactions. Regardless of the particular solute being considered, separation of the solute particles from one another requires an input of energy to overcome their attractive interactions. The process, therefore, endothermic. Separation of solvent molecules to accommodate the solute always requires energy. The third component, which arises from the attractive interactions between the solvent, the solute, and the solute, is always exothermic. As shown in Figure 13.4, the three enthalpy terms in equation 13.1 can be added together to give either a negative or a positive sum, depending on the relative magnitudes of the terms. Thus, the formation of a solution can either be exothermic or endothermic. For example, when magnesium sulfate, MgSO4, is added to water, the resultant solution gets quite warm. In contrast, the dissolution of ammonium nitrate is endothermic. These particular substances have been used to make instant heat packs and ice packs that are used to treat athletic injuries. The packs consist of a pouch of water and a dry chemical, magnesium sulfate for hot packs and ammonium nitrate for cold packs. When the pack is squeezed, the seal separating the solid from the water is broken and a solution forms, either increasing and decreasing in temperature. In Chapter 5, we learned that the enthalpy change in a process can provide information about the extent to which a process will occur. Processes that are exothermic tend to proceed spontaneously. A solution will not form if the heat of solution is too endothermic. The solute-solvent interaction must be strong enough to make the delta H comparable in magnitude to the first two heat of solutions. This fact explains why ionic solutes such as salt do not dissolve in nonpolar liquids such as gasoline. The nonpolar hydrocarbon molecules of the gas would experience only weak attractive interactions with the ions, and these interactions would not compensate for the energies required to separate the ions from one another. By similar reasoning, a polar liquid such as water does not form solutions with a nonpolar liquid such as octane. The water molecules experience strong hydrogen bonding interactions with one another. These attractive forces must be overcome to disperse the water throughout the nonpolar liquid. The energy required to separate the water molecules is not recovered in the form of attractive interactions between water and C8H18 molecules. Solution formation, spontaneity, and entropy. When carbon tetrachloride and hexane are mixed, they dissolve in one another in all proportions. Both substances are nonpolar, and they have similar boiling points. It's therefore reasonable to suppose that the magnitudes of the attractive forces, which are London dispersion forces, among the molecules in the two substances and in their solution are comparable. When the two substances are mixed, dissolving occurs spontaneously. That is, it occurs without any extra input of energy from outside the system. Processes that occur spontaneously involve two distinct factors. The most obvious factor is energy, which we've just used to analyze the dissolving of sodium chloride in water. The other factor is the distribution of each component into a larger volume, the tendency in nature for substances to mix and to spread out into larger volumes. We see the influence of energy all around us. If you let go of a book, it falls to the floor because of gravity. At its initial height, the book has a higher potential energy than it does when it hits the floor. Unless the book is restrained, it falls, and as it does, potential energy is converted into kinetic energy. When the book strikes the floor, the kinetic energy is converted into largely heat energy, which is dispersed throughout the surroundings. The book has lost energy due to its surroundings in this process. The fact leads us to the first basic identifying spontaneous processes and the directions they take. Processes in which energy content of a system decreases tends to occur spontaneously. Spontaneous processes tend to be exothermic. Change tends to occur in the direction that leads towards lower energy or lower enthalpy for the system. Some spontaneous processes, however, do not result in lower energy for a system, and even some endothermic processes occur spontaneously. For example, ammonium nitrate readily dissolves in water even though the solution process is endothermic. Processes such as these are characterized by a more dispersed state of the one or more components, resulting in an overall increase in the randomness of the system. In this example, the densely ordered solid, ammonium nitrate, is dispersed throughout the solution as separated ammonium and nitrate ions. The mixing of carbon tetrachloride and hexane provides another simple example. Suppose that we could suddenly remove a barrier that separates 500 mL of carbon tetrachloride from 500 milliliters of hexane, as shown in figure 13.6. Before the barrier is removed, each liquid occupies a volume of 500 milliliters. All of the carbon tetrachloride molecules are in the 500 milliliters to the left of the barrier, and all of the hexane molecules are in the 500 mL to the right. When equilibrium has been established after the barrier is removed, the two liquids together occupy a volume that's about 1,000 milliliters. Formation of a homogeneous solution has increased the degree of dispersal or randomness because the molecules of each substance are now mixed and distributed in a volume twice as large as that which they occupied individually before mixing. The degree of randomness in the system, sometimes referred to as disorder, is given by a thermodynamic quality called entropy. This example illustrates our second basic principle. Processes occurring at a constant temperature in which the randomness or dispersal in space, or entropy, of the system increases tend to occur spontaneously. When molecules of different types are brought together, mixing, hence an increased dispersal, occurs spontaneously unless the molecules are restrained by sufficiently strong intermolecular forces or by physical barriers. Thus, gases spontaneously mix and expand unless restrained by their containers. In this case, intermolecular forces are too weak to restrain the molecules. However, because strong bonds hold sodium chloride ions together, sodium chloride does not spontaneously dissolve in gasoline. We'll discuss spontaneous processes again in Chapter 19. At that time, we'll consider the balance between tendencies towards lower enthalpy and towards increased entropy in greater detail. For the moment, we need to be aware that the solution processes involve two factors, a change in enthalpy and a change in entropy. In most cases, the formations of solutions is favored by an increase in entropy that accompanies mixing. Consequently, a solution will form unless solute-solvents or solvent-solvent interactions are too strong relative to the solute-solvent interactions. Solution formation and chemical reactions. In all our discussions of solutions, we must be careful to distinguish the physical processes of solution formation from chemical reactions that lead to a solution. For example, nickel metal is dissolved in contact with hydrochloric acid solution because of the following chemical reaction occurs. Nickel plus hydrochloric acid yields nickel 2 chloride plus hydrogen gas. In this instance, the chemical form of the substance being dissolved is changed from nickel to nickel 2 chloride. If the solution is evaporated to dryness, nickel 2 chloride 6 hydrate, not nickel, is recovered. When sodium chloride is dissolved in water, on the other hand, no chemical reaction occurs. If the solution is evaporated to dryness, sodium chloride is recovered. Our focus throughout this chapter is on solutions from which the solute can be recovered unchanged from its solution.